Organizing committee for giving me the opportunity of showing some of our results. And thank you people to stay till the last minute of the conference. So I'm Albino Aguiar from the Peace Department in Federal University of Pernambuco. And I have to press here. Talk about bulk materials, new bulk materials, and possible new band superconductor. The idea is, so just to show you, Arcadi mentioned something about Recife, and I just want to address two more points. We are on the corner of the South America. It's the closest point to Africa and to Europe. And Recife is well known for his carnival and cultural activities. And we have been trying to develop research there since 30 years ago. Yeah. And we are there now that Arcadi is joining us. So I'll give you a brief introduction. I'll talk about this compound, zirconium 1 - X, vanadium X, and then I'll go to the niobium doped material, and I'll do a summary. So this is the place where Arcadi is planning to organize the conference in 2 years. Okay. There are a list of people that we are collaborating. So these people, you see, Zach Fist, I put him in Brazil. Where is it? Yeah. So these are people that work close to, between São Paulo city and Rio de Janeiro city. It's and Zach Fisk has strong collaboration with them. Then we have people doing theory in Recife, and we have collaboration with Belgium, with Leuven. And also we have people in Recife working, of course. Okay. So, metal diborides. They are very interesting materials because they have layered structure. So, we have since long time ago that people tried to grow, to make these materials. And the first, as far as I know, trial was by electron structure calculation, and they predicted that this material, silver diboride and gold diboride, they would have this transition temperature very high compared to for example, for manganese diboride. This was not, there is no experimental confirmation at all till the moment. And also, yeah, this was realized in niobium almost diboride, yeah, 1.94, but the transition temperature is very low. These people, Leia Roviska and Leia Rovisky, they studied all these compounds. Yeah? Metal boron 2 with titanium, zirconium, hafnium, vanadium, niobium, tantalum, chromium, and molybdenum. And they found only superconductivity for niobium boron 2 at a very, very low temperature. Okay, then we had Akimitsu discovery of superconductivity in magnesium diboride, and it was shown that these two gaps, for example, I choose this result where you have the heat capacity compared with one gap model theory and two gaps, and you see that it fits. And then later on, we have to get clearly detected. So we decide to look before. So there is one report about superconductivity in zirconium boron 2. It was a transition temperature of 5.5 and also with thallium, niobium. But you see here, this is the X-ray diffractometer for this material. You see the impurity phase, and this impurity phase is due to zirconium dot decaborate. That is superconducting at about 6K. So we have a look. So these guys, Pereira et al., they found no superconducting transition in either vanadium boron 2 or zirconium boron 2. So we decide to look at this material, and we decide to prepare zirconium 1 X, metal X, boron 2 to get this kind of material. We start both vanadium substitution and niobium substitution. And these are the concentration. Okay? This is the phase diagram for zircon boron, and you see that the only phase possible is zirconium boron 2. And we have also the phase diagram for niobium boron, and you can form niobium boron to a very high temperature if you go to the authentic point. So this material were done by melting the pure metal, and we developed a very nice oven to prevent any contamination. So here is the X-ray for zirconium 0.95, vanadium 0.05. This was published last year, and you see that we can index all the peaks in aluminum 2 boron 2 prototypes. For all concentration we studied, we can zoom here, and we have the same structure. So we see no trace of zirconium boron 12. This is very important. Okay? If you draw the lapse parameter as a function of the vanadium concentration, you see that the A parameter is constant with doping, but the C parameter decreases. And then when you reach about 0.05, it is it's still constant, there is no variation. So this is an indication that we have a solubility limit of 5% in this material. So when you are doping, you are compressing the CX. So there is a compression of the unit cell. So now that we have structural data, let's look at magnetic data. So these are the temperature dependence of the magnetization in FC, ZFC scheme. And you see that all samples scattered, 1%, 2%, 4%, 3%, vanadium dopant. We have a clear superconducting transition. We have the immiscibility line. The inset we show M versus H. And for example, for this sample here, we have a double transition. Maybe there is a mixed phase. We did not identify this. But if you draw the critical temperature as a function of concentration, you see that there is a maximum that coincides with the solubility limit. So we decide to look for this sample in more detail. So this slide, I again reproduce the magnetic data. And here we have the resistivity data. You see also that it's a clear resistive transition. So we have no doubt that this is indeed superconducting material. And I have to call your attention. Look at these numbers. This is a very, very good metal. Resistivity here is 2.5 times 10 to minus 8. Copper is 1.7 at room temperature. 1.7 times 10 to minus 8. This is very, very good metal. To make this measurement and as a function of field is very hard. It's not easy in this material. Also, this kind of material I discovered later. They are very, very, very hard materials, and they are useless as to cover the nose of airplanes as a layer. Okay. Again, at zero field for the same sample, we have the heat capacity data. And you see there is a fitting, you see that there is a jump at the transition temperature. So we have no doubt that this is a bulk superconductor. If you subtract the phonon contribution, you get this. Now let's go to see what we get for the upper critical field. So these are the measurements that I mentioned that they are very tough. This you have the resistivity transition as a function of field. And this is for the 0.96% of zirconium field increase in this direction. And if you use the Wertheimer-Helmholtz from Hornberg model, you can fit like this. You can, I call your attention that it doesn't fit well, just here close to see. But just to have some numbers, we get very high Hc2 field at zero temperature for this material. Let me put it here.
What are the units?
Teslas. Yeah. Here it's in Oersten for the Hc1. So we measure just take the derivative for NH curves, and then we define when the theoretical, the line difference by 10 to minus 7 from the experimental one, we define the HC1, and you have this kind of behavior. This kind of behavior suggests some interpretation. So we try to make a fit with this law and get template Oersten for this field. And then we look for some theory. You can find many of them to fit with two bands. And this is very interesting. You can think if you have contribution from the pi band and the sigma band. One with high and another one with low Hc2. So if you put this together, again, the heat capacity, and here I reproduce this data, but here I show that it doesn't fit with BCS theory. Okay? So now I compare, but I will skip this, I'll come later. And I move now. So we claim that this is unconventional superconductivity, mainly based on the AC1 behavior and the heat capacity data. And we also have done some JC, critical current measurement. This was published in this article. So again, you make these curves, you take delta M and use beam model. W and B are the sample parameter. And we can see that exponential, we can fit, and you can calculate the pinning force, and you see that it fits well with a double exponential method, indicating that indeed we need two band. Of course, I'm not proving that it's a two band. We still need to do more experiments, and we did single crystal. These are not single crystal. But I have some, okay, so these are the reference of this data. And we succeed in making a very tiny single crystal. And I'll show you the result. We could not reproduce the result because we broke the single crystal. So we are trying. So this is the X-ray refractogram. Show that indeed this is for X close to 0.04. And what? This is wrong. This is wrong. So you have the temperature details of the magnetization as a function of field. When you apply the field parallel to the Cx on the left, and you have two-step transition. We claim that this is one transition, this is another transition. When you look here for the field parallel to the AB plane, you don't see it. Yeah? Okay. So, our question is this. Is this evidence of two gaps? How many minutes?
10 minutes plus 2-3 minutes for questions.
Okay.
Still capable.
So, we don't know, but if we agree that it is evidence for two gaps, then you can do this. You can draw your S, the first critical field dependence, temperature dependence. If you draw a contribution from the pi band and the sigma band like this, you would fit the data. Yeah, of course, we need to measure the gap in this material.
Why you don't see the thing inside?
It's a good question. I return to this point. Yeah. One possibility is that we have, I don't have for this sample, maybe we have a mixed phase that is aligned with CS, but I don't know. Yeah? So this is for this material. This fits well. I can tell you that.
Sorry, this HC1 is for the single crystal.
This is for the single crystal. This is single crystal data. Yeah? We are working to, it's not easy to get big single crystal and uniform. So we decide to look for another material and come to there. And we decide to look for niobium. And here you see the X-ray refractogram for this material. And you see that we have some zirconium impurity here. But zirconium is not superconductor, so there's no problem for us. You can make the rocking cube, and then you see that, sorry, it's in Portuguese, but you can understand this intensity, and this is increasing dopant concentration. The peak moves to the right, so it's a proof that we have changing the density parameter. We do width value refinement, for example, for this sample, and we can fit everything perfectly. All the so this is so we can get the A parameter as a function of diagonal concentration, and it decreases linearly. Also the C parameter. Yeah. You see that it's different from the vanadium one. The vanadium, the E parameter stay constant as the doping concentration, and the C decrease, and you have a solubility limit. Here, as far as to this concentration, we have no solubility limit. But if you put together these two, you indeed have a decrease of the unit cell. Yeah, it's the same. We have compression. In the case of vanadium, we have a C compression, but here the whole cell is compressed. Okay. So we have a 2% compression in the A, yeah, and I compare with zirconium, 8%. Here we have EDX showing, apart from this sample, we have some holes. Here, the sample I showed the data is this one, is 4%. We have some grain boundaries here, and this can be due to different phase. And since it's oriented, we see it can be. We cannot rule out that we have this kind of thing. So the magnetic data for this material, you see clearly that is superconducting. Yeah. So this magnetization M versus H, all of them were taken at 1.7. Okay. Again, here we have the transition temperature as a function of concentration, and it seems that for this concentration we have the optimum doping. What do we have here? Okay, this is again magnetization at several temperatures for this cube. It's very low pinning. And to determine the first critical field. Again, you have the same kind of behavior. You can think on having one like this and another like this. Two contributions. I'm coming to the end.
3 minutes.
I think I'll finish in one. So the resistive transition at zero field and the heat capacity. You see that it's a smaller jump. For the other one with vanadium, we have for gamma 3.8, here it's 2.1. The coherent length for both samples is of the order, you can take it from the second critical field, it's of the order of 4 angstrom, 4.5. Again, here the data to get the AC2, you can fit, and then you get, it's high. It should be here, not here. So, want to have more, the transition for all the sample, and finally, let me show this is transition temperature. We decided to start the pressure dependence of the temperature. And we have for two samples, niobium sample, doped, and they have the same dependence. And we have a change from 0.5 K. Yeah. Arkady is trying to model this. And here are the data. You see that it's quite robust. Superconducting transition. And here again is the dependence of the second critical field with temperature for different pressure. Yeah. So I'm going this. Yeah, this is for the sample, and you have the same qualitative behavior. And then I come to my conclusion or summary. We succeed to prepare polycrystalline. You see that I don't speak here about the single crystal. Yeah. And what we proved is that vanadium and niobium are indeed able to induce superconductivity in this non-superconducting material. And we have evidence that is unconventional. If it's true, then as we suggest, it's not proved yet. And I would like to mention this. You talk about engineering this, yeah? So I'm quite convinced that it's still for new two band material. We have to dig there, maybe you can find.
Yeah, no sharks there.
No sharks, just yellowfish. Just
No proximity of sharks.
Those are piranhas.
So these are the people in Recife. Arcado was not in this picture, I don't know why.
You can Photoshop it.
Yeah.
Maybe I did not.
And okay, we have postdoctoral, and we are seriously involved in prepare the MultiSuper for 2016. Finally, I have to mention the people who pays the bill, yeah. And this I have to mention you what means this. This in Portuguese means knife, yeah. But this faca is knife. But this means the foundation for supporting the scientist Albino, that is me.
Okay. Thank you. Because in the presentation we have two questions, possibilities. Any questions?
Yes. From a theoretical standpoint, it's difficult to comment on polycrystalline sample.
Yeah.
For single crystal, you had this HC1 versus temperature curve. Did you try to fit it with, say, Askizar expression?
Just by him. Imagine.
You have already DCs right out.
Yeah, but I would like to tell you that I still don't really believe in my single crystal. I'm working to be sure that it's really single, there is no inclusion of any other phase. I can try, but if I don't show you a gap measurement, you will not believe me. Nobody. Neither I.
I have a comment. My question. Albino, can you show the HC2 behavior?
HC2.
Yes, this figure.
Okay.
You see that, in fact, for me, it's no doubt that this is multi-band superconductor because HC2 has these features close to TC. So this fit actually, this is just guide for the, nothing more.
No.
If you start to fit data which are close to the TC, so the line behavior will go much lower.
Yeah.
So to fit this data, you need to introduce extra terms. It means that this is not the case in the usual BCS, one-band superconductor. Sorry? This is single crystalline.
This is a single crystal.
This one.
Yes.
Okay. We can discuss later.
Yeah.
We have to move, no? Yeah. Okay. You want to?
Yes, this is single crystalline.
No, that one is polycrystalline.
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 Okay,
Yeah.
that's different.
Yeah.
Yeah. Okay, any other questions?
I just want to notice that when you say unconventional, in the sense of superconductivity, we say unconventional where it breaks additional symmetries to U1. So a superconductor means that is in more than one band superconductor, it's not unconventional. So, but nevertheless, you had some scaling relations at low temperature.
Yeah.
But there you have to look for whether there are, scaling factors.
Sure. I agree.
Okay. Okay, let's think again.